very famous story in physics circles. Maybe some of you have heard about it. In 1870s, there was a young guy who was thinking about his PhD topic, and he couldn't decide what he should study. So he went up to his supervisor, and he's like, I think I should take up theoretical physics. And his supervisor was like, यार वो कोई पढ़ने वाली चीज़ है, उसमें तो सब कुछ discover हो गया, जो होना था वो हो गया. Like you can't do anything more in it. Anything that had to happen in physics has happened. It's a dead topic, so you should change your track. I think that guy really took it to heart. Because that was the time when we came to know about the entire theory of radioactivity, and we came to know about the entire quantum theory. And आज तक अपनी high school की books में we study about Planck's constant, we study about Planck's formula, and it's all thanks to this one guy that we are here in this workshop, and we are going to study about quantum computers and how they are advanced enough to implement artificial intelligence models. So let me overview quickly कि आज की workshop में हम लोग क्या सीखने वाले हैं. So we are going to learn about some basic building blocks of quantum computers. Because अभी उन्होंने पूछा था how many of you are aware, so apparently a lot of you are not aware with how quantum computers work. So we'll overview a bit of that. And then we will look at two libraries by Google, TensorFlow Quantum and Cirq, which you can use to actually build quantum circuits and quantum models in your laptops. And then we will look at a demonstration and discuss some good things about it. So the first thing that I want to talk about is the qubit. How many of you know bits? Everybody knows bits, right? A bit is a basic unit of information in the computers we have today. So a quantum bit is a fundamental unit of information in a quantum computer. But the difference is that a classical bit is either a 0 or a 1. But a quantum bit is a 0, a 1, everything in between, and all of them and none of them at the same time. Did that make sense? So a misconception about quantum bits that a lot of people reiterate is that quantum bits are neither 0 or 1, or that they are a value in between. So they don't take a value of 0, 1, but they take a value in between. But I think this is a more accurate representation, because the truth is that they are in a superposition of all the values at the same time. So this is why we have to make separate gates for them. How many of you know about simple logic gates? Right, so we have an AND gate, we have an OR gate, we want to add the bits, we want to subtract the bits, we want to flip the bits, we use classical gates. But for quantum bits or qubits, we have to use quantum gates because they exist in a superposition of states, so there are some different mathematical operations that we have to perform in them. Back there, they were telling me that for every formula you show on a slide, you lose half of your audience. So I think in the next slide, I'm going to show you 5 formulas altogether. I know it looks really scary, but it is actually very simple if we go through it in this way, that this is just a gate, and it just performs an operation. We don't care how complicated it is, because our calculation will be done by a computer. Thankfully, we don't have to calculate this. We just have to tell our computer, T-gate bana do yaar, theek hai? We just have to tell it, aap ek control NOT gate bana do. We just have to put the code in. It will do all of this. We don't have to do it, right? And it will give us the output. So the basic things we can do with a qubit is we can flip them, we can flip the bits, we can flip their phase. And then there are 2 things that we can do with quantum bits that we can't do with classical bits, is that we can entangle them together, and then we can also create superpositions. So how many of you know about quantum entanglement? See, it is a very interesting concept, and if I have to describe it in one line, it is when 2 qubits are connected enough to transfer their data to each other without actually having any sort of physical connection between them. And before you guys ask me कि ये कैसे हो सकता है, ये मुझे भी नहीं पता, ये किसी scientist को भी नहीं पता, it is still a mystery to this day. We just know that it exists, that there are some qubits that can communicate with each other without any form of network in between. So they don't have Wi-Fi, they don't call each other, they don't text each other. But if you give some sort of information to one bit, another bit would know it at that instant. So that is something useful for information transfer, and that is why we have the Hadamard gate that creates this entanglement, right? And so using bits and using gates, we can create simple quantum circuits like we create logic gate circuits for classical computers. So if I show you an example, this is what a quantum circuit would look like, right? I think you guys are familiar with this structure if you have studied some sort of hardware or computer architecture courses, I'm not sure. But if you look at a basic classical computer, it looks like this, except that the gates we are using are just, your classical gates, but over here we have the Hadamard gate that creates entanglements, and then we have the T gate that creates superpositions. So then this is a circuit or a quantum circuit that is at the core of a quantum computer. I think we're all good with that. So this is the slide which I think can, if you understand what is going on over here, you can understand all of quantum theory, quantum computing, quantum machine learning, quantum AI, and quantum physics, and all of these 4 different domains in this one slide. So how many of you know about this experiment from school? I think a lot of you, or college, right? We've studied this experiment. Nothing is happening over here. We just have the wave-particle duality nature, and it is being proved in this experiment. So if we pass electrons through a slit, they act like particles, but when we catch them on the screen, they act like waves because they create constructive interferences. Do I have to explain what is a constructive interference? How many people think I should explain what is a constructive interference? It's basically when 2 electrons like each other and they become friends and then they amplify their signal. And when they dislike each other, they create a destructive interference when they get away from each other, and then we don't, perceive any signal. So what we are doing over here is we are on this screen detecting which particles became friends and which, hated each other and disappeared and did not, communicate any signal. So our purpose in building quantum computers and in building quantum algorithms and building quantum machine learning theories is it is just one thing. We want to create a constructive interference that is so great that it outnumbers all of the other possibilities. So the particles that we receive have such a positive impact that all of the other particles, all of the other interferences and patterns that we receive, we want to dull them out, and we want to receive the one that had the highest amount of constructive interference, or that had the highest amount of positive impact or output on our result. And in quantum machine learning, we just do iterations to find the most optimum way to create these interferences. For example, in our classical neural networks, like the talk before me, they talked about neural networks and their structures, and we saw that in classical neural networks, what we have to do is we have to do iterations to find the right gradient. How many of you know about gradient descent? Yeah, quite a lot of you, right? So we have to find the correct parameters. We have to do iterations to do that. In quantum machine learning, we do iterations to find the perfect way to have the most amount of constructive interference. So this is the core of quantum machine learning, right? So this is a classical image classification example. There was a lot of good stuff about it in the previous talk related to OCR. This is exactly the structure that we use, but you guys would have noticed that we have some additional vectors, some additional gates over here, and some notation that you are not familiar with in classical computers. So what we normally do is we take an image, we divide it into pixels, and then we take those pixels, we assign a bit to them. This is what we do in image processing. How many of you have done image processing or any sort of OCR? So this is what we do, right? We break the image into pixels, right? And we give every pixel a bit. Over here, we break the image into pixels, and then we give every pixel a vector state, and then every vector state is assigned a qubit. That is what we are doing. And then when it transfers into the quantum realm, we apply some formulas to it, and then we are able to have the same amount of probability output. For example, in this model, it is giving me 0.3% probability that that picture is probably a dog, right? So this is the basic framework that we follow. So moving forward, we would, towards the end of this workshop, we would demonstrate how do you actually code for this, right? Because this is a workshop and I wanted to show you something that you could make and go home and experiment with and learn more about quantum circuits. So the two libraries that we are going to talk about, number one, we have TensorFlow. That's all of our favorite library. I'm pretty sure everyone knows about TensorFlow at this point, right? Keras, TensorFlow, it's a great library for implementing classification algorithms, classical algorithms. I think this mic is... मेरी आवाज़ आ रही है ना? Yeah, okay, great. So TensorFlow came out with a library, or you can say a package, specifically for quantum machine learning, and it is called TensorFlow Quantum. So these are two great tools that you can use to completely implement any sort of quantum project that you want. So you wouldn't need any additional stuff, right? So with Cirq, you can build the circuit, and then you can feed the circuit into TensorFlow Quantum, and you can train a machine learning algorithm on the circuit that you built, and then you can read your results. These quantum computers are very hard to make. They require a lot of intensive hardware, and they're very expensive to make, and there are very few facilities in the world that actually do have running quantum computers. So Google has one, IBM has one, right? And there are some Chinese companies that have some, but like that is about it, right? So all of the circuits that you make and all of the algorithms that you run, they actually directly do go to that one quantum computer in the Google lab, and then they run on it. So this is something really cool. You can directly access that quantum computer, and these libraries are completely free to use. This is a basic structural example of what I was saying. So you can make, this is the circuit part. These are some scary looking symbols, but these just represent gates that we talked about. So these are some gates. These are some vectors. These are some mathematical operations. You can build this entire circuit in Cirq. And then this is the part you are already familiar with. You build a neural network. You take samples. You take averages. And then you can evaluate your cost function. And it's just very doable. So before I move forward, I want to tell you something about the demonstration that we're going to do is that, so to use these libraries, the demonstration that I have prepared, this is on Jupyter Notebook, right? And this mostly, TensorFlow is a Python library, and these work great with Python. ठीक है, तो if you are familiar with Python programming, if you have used Jupyter Notebooks, you can also do this in any sort of IDE, but this is prepared on Jupyter Notebooks. So what you have to do is simply you have to install TensorFlow, and then you have to install TensorFlow Quantum, and then you have to import Cirq, and then you have to set up your environment. The thing that you should remember is that there are some package compatibility issues that you should remember is that TensorFlow 3.10 वाले Python के जितने भी उसके बाद वाले versions उनके साथ नहीं चलती. So I know that is very annoying, and I actually hope that since this is the Google DevFest and some people are from Google are from here, so they're listening to me, can you please upgrade TensorFlow? ठीक है, Python जो है वो 3.15 तक आ चुकी है, but TensorFlow 3.10 तक चलता है, तो आपके कंप्यूटर पे 3.15 होगी, you have to roll back to 3.10, and then you have to get TensorFlow version 2.7, and then TensorFlow Quantum version 7.2, and you have to set up your environment. Okay? And then how many of you have worked with the MNIST data set? It is a very common practice data set that, so we're using the same data set, so I hope that a lot of people would be familiar with it, right? So we are simply loading the data set. So this is the code that I've used to load the training and testing examples, and then this is the output. ठीक है, उसके बाद, oh, we are lost, right. अच्छा, उसके बाद what we are doing is, so अच्छा, for those of you who don't know, MNIST is a data set that contains a database of handwritten numbers. So you run your algorithm to recognize or identify those numbers, right? So we are filtering down to number 3 and 6 only. So हम 3 और 6 की क्लासिफिकेशन करेंगे एंड वी आर डिस्कार्डिंग द रेस्ट ऑफ देम. क्यों कर रहे हैं डिस्कार्ड वो मैं आपको बाद में बताऊंगी, बट दिस इज बेसिकली व्हाट यू डू टू डिस्कार्ड इट, राइट? एंड so this is the image that we have from the data set that I've pulled. You can use the code to show it. Acha, so the next step that we have to do is we have to downscale that image. So this is the number 3, the image from the data set, and then we downscale it, and this is also number 3. Like you can't tell, but it is, theek hai? And can someone tell why did we have to do this step? Like I gave a little bit of a tidbit before we started. Sure. Exactly. Like I told you, quantum hardware is very rare, it is very expensive, very difficult to build, very less available, and we don't have very high-powered quantum processors. So if you use full resolution images, it won't run. Okay? Like your hardware wouldn't be able to handle it. So you have to use very small 28x28 images. So we have to downscale the images to a very low resolution version to the point that they look like this. Okay? And then the thing that we have to do is that we have to convert our data into quantum bits. So this is a new part, so I'll spend some time on it. Because normally at this point you would just start, training your data set, but we can't do that for quantum machine learning algorithms because they need quantum inputs. So what do? We convert our image pixels, we assign them to qubits. And it is very simple, like I showed you the entire page full of formulas. I just had to pull these 2 functions and it will do all of that. Okay? So we set a threshold. Why do we set a threshold? Because any qubit that is above the value of the threshold, we will have to use an xgate to flip it, ताकि वो threshold की value से नीचे रहे. So remember to set a threshold. ठीक है, and then remember to implement an xgate. तो मैंने क्या कहा था, सर्किट बनाने के लिए हम Cirq यूज़ करते हैं, तो we need an xgate. xgate के लिए हमने Cirq पुल किया है, ठीक है, we are simply using the inbuilt function to implement the xgate. The xgate function is called x. It's that simple to remember. So you can just pull circ.x and then you can add it in your layer. So like we are implementing the xgate onto our qubits. So जो भी threshold से ऊपर होगी, they'll get flipped, right? So this is what it looks like. You can run the command svg circuit to actually see कि आपने बनाया क्या है. और ये असल में गूगल का जो क्वांटम कंप्यूटर है उसके अंदर सर्किट उसकी हार्डवेयर के अंदर ये बना है. ठीक है, आपने ये एक एक्सगेट बनाया, उसके अंदर आपने वो 2 इनपुट्स दिए हैं. दिस इज द सर्किट यू आर डूइंग. ठीक है, उसके बाद आप इन सर्किट्स को टेंसरफ्लो के अंदर फीड कर दो. ठीक है, सो यू हैव टू यूज tfq.convert simply to transfer it to TensorFlow. ठीक है, and then you can build the model circuit in TensorFlow to run your machine learning algorithm in. So for example, I've used the circuit layer builder, and you can add the circuit layer by layer. ठीक है, so we've added some xgates over here. We've added some xgates for the 0-0 input, for the 1-0 input, 2-0 input, 3-0 input. And now you guys must be wondering कि हमें कैसे पता चलेगा कि हमने यहाँ पे क्या क्या कुछ डालना है. तो a lot of this you have to learn by reading the documentation and having some theoretical knowledge of quantum physics, but it would still work if you knew nothing and you went to the code labs website today and you ran this code, because a lot of this is automatic. So for example, मुझे तो पता है कि ये यहाँ पे ये xgate मैंने डालना था क्योंकि डेटा की इनकोडिंग करनी थी, but if you just go and pull the function of add layer, ठीक है, आपको बस ये पता होना चाहिए कि add layer के parameters क्या क्या हैं. अगर आपको ये नहीं भी पता ना कि उस layer ने add क्या करना है, you just pull the function और वो आपको ये circuit बना देगी. ठीक है, literally आप बस svg circuit ब्रैकेट सर्किट का कमांड लिखो, इट विल शो यू उसने क्या बनाया है. मतलब ये भी हो सकता है कि आपको खुद नहीं पता है, आपने फंक्शन लिखा है, उसके बाद उसको विजुअलाइज किया एंड देन यू फाइंड आउट कि अच्छा ये बन गया उसके अंदर. ठीक है, एंड देन दिस इज सम हेफ्टी. अच्छा, सो दिस इज सम इम्पोर्टेंट, the main part, which is the quantum neural network, right? So for normal neural networks, we have some TensorFlow functions where you can just import them. They have pre-built neural networks. The same is true about the TensorFlow Quantum package. For example, you can just load your data from Cirq, right? And then you can use the builder layers function, It literally works like TensorFlow normally works, right? You can use the builder layer functions and you can add layers into your neural network. And then what you do is, how many of you know about Keras, right? We use TensorFlow with Keras, right? So you can add the wrapping with Keras as well. You simply use the tf.keras function. I'm not going into the detail of this because अब आगे सारा TensorFlow वाला काम है, so we've converted. And then you can modify for hinge loss. For those of you who don't know, hinge loss is what we have to take care of when we're doing gradient classification. So you can add some functions for that. You can customize the hinge accuracy according to your needs. And then you can print the model summary to see what model you have. For example, we have a model with 32 parameters, and they are all trainable. So you can actually print important information that you need. Okay? And then you can train the quantum model. For that, you have to use the train, X-train, and Y-train functions. It's as simple as that. Okay? And then you are training. And if you train to convergence, so these are the results that we receive, right? So then we have about a great, like 80 to 90, on average 85% accuracy, which is pretty good for classification. So if you want to compare with a classical model, ठीक है, आप एक classical model import करो TensorFlow में, normally जिस तरह model बनाते हो बनाओ, print their accuracy, ठीक है, and now what do you think? What do you think? Where is the accuracy? Like, who's winning the accuracy showdown? The quantum model actually loses by a very big margin. So then what were we doing this entire time, right? Okay? Like, we went through all of this extra attention, okay, all of that extra hard work, only to create a model that has way less accuracy than already existing models that we could have easily used on the entire data set, right? So is cheese ka point kya tha? Well, the point is that classical models are good for classical data, but in our world, all data is not classical. And classical data cannot learn quantum data sets, okay? So if you have an application where you have quantum data, and you guys would be thinking, quantum data कहाँ पे होता है, ठीक है? हर जगह पे classical data होता है, जो हमें अपनी आम जिंदगी में चीज़ें चाहिए, वो सब classical data होती हैं. तो हम क्या करें quantum data के बारे में, you know, हम ये model experiment और ये क्यों करेंगे सब कुछ? So the thing is that quantum data is actually at a lot of places that we don't even think about, क्योंकि जब तक quantum machine learning exist नहीं करी थी ना, किसी ने कभी ये सोचा भी नहीं था कि अच्छा हम इस data को भी किसी तरह से use कर सकते हैं, and we can actually make useful applications for it. So that's the first thing. We need quantum models for quantum data. And the second thing is that if we make a hybrid model, where we take the best parts of a quantum neural network and a classical neural network and build a hybrid neural network, we would have achieved an accuracy that sometimes goes up to 100%. So for example, इसी data set के अंदर, if you convert this data to quantum data first, before feeding it into the model, so these are the steps to do that. So you can see that with the classical and quantum hybrid, we are able to achieve the highest accuracy, which is greater than quantum and classical separately, right? And then other than that, let me take it. And the second part about who has quantum data, so in our world, sabse pehle, chemists have quantum data. People who do chemistry, people who are doing drug discovery, people who need to understand structures of molecules, they have quantum data. And because quantum machine learning is a thing now, they can actually generate information on new molecules, and they can generate new drugs, they can discover new drugs because of these models. So for example, this is a result from a paper where you can see the accuracy and the results are very high, where the quantum neural network helped them discover a new molecular structure which could help them develop better drugs for the treatment of autoimmune diseases. So that is a big, big breakthrough, right? And then this is a result from a paper that conducted research from classical and quantum models combined, and they were able to achieve 100% accuracy on detection of the number 3 and number 6, which are pretty hard to detect in classical models, right? So the other examples of quantum data is high energy physics in world labs like CERN, people who are developing things in physics and rocket and space science, they have a lot of quantum data. Quantum neural networks can help with that. And high dimensional signal processing, the data from our voice the data from the noise, the data from people speaking is also actually not classical at a lot of times. But with quantum machine learning, we can now process voice and audio data in a better way because there are a lot of quantum dimensions to it. So the entire field of signal processing, so signal processing is everywhere. It's in videography, it's in laptops, it's in phones, can benefit from it, right? So what's next for quantum, Like, we are at a very low stage right now in development, so what's next? Like, agle 10 saal mein, 20 saal mein, where is quantum machine learning going? No, it's never going there. That's not possible. That is not going to happen. But where we are going is we are going towards enhanced machine learning models. We are going towards specific applications like network attacks, financial modeling, drug discovery, molecular modeling, and we are going towards better hardware development and better algorithmic developments. So that was all from my side. Thank you everyone for being patient. We don't have, I think, enough time for Q&A, so if you guys want to reach out, there's my LinkedIn at the bottom. You can throw in any questions, anything you want to learn about quantum computing. And all of this code is also available at Google Colabs. So if you guys are familiar with Google Colabs, you can just go to the TensorFlow, you can just Google that. Go to TensorFlow's Quantum's introduction page, and you can find a lot of tutorials, and you can go home and make a quantum circuit in your laptop today. So that would be really cool. Thank you so much.